Hello friends, welcome to my video. Today I am going to show you and explain you the working of a Tesla coil using a Slayer exciter circuit. I built this out with very cheap components available easily in the market. Here's how it works. You can see the CFL light bulb wirelessly turning on, so that means there's a wireless power transmission. All I'm using is a 12 volt battery charger and a little components here. What I'll do is in this video I will take you through the schematics and then I'll show you the actual build as we see the schematics. Alright, let's get onto the board. What I've drawn here is I hope you can see this, is the schematic of a Slayer exciter circuit. The way I'm going to explain this today is break down each and every component. Okay, now what our objective in the Tesla coil or in a Slayer exciter circuit is to charge or to transmit power wirelessly to a light bulb, for example, which is also called as a top load. Okay, now to transmit power wirelessly you need to have a very high voltage, high enough that it can bridge the air gap between the load and the output. The way it bridges the air gap due to high voltage is that it ionizes the air and then transmits power to the load. What I've done to achieve this is I've built a homemade step up transformer, which is this here. How I've done that is I have essentially taken 500 turns of a secondary winding across a 1-inch diameter pipe, PVC pipe, which is 20 centimeter long. So take 500 turns. The wire that I've used is 29 AWG copper insulated wire. It is a tedious task to wind it around. Care has to be taken in 2 or 3 aspects. Number one, the windings has to be tight so that they don't slip. So what I did is after every 100 turns or every 75 turns or whatever, you tape it. Okay. Number two, it's very important that you don't wind the wire over each other. This is a common pitfall that new Tesla coilers do, is in the rush or in being impatient, they wind it over each other, and then that doesn't do the job at all. It should not wind over each other so that the polarities don't cancel out. Okay, it's very essential. And so this is essentially the secondary winding. And then you have to do a primary winding, which is a normal multi-strand wire that you can get at electronic stores. This doesn't have to be copper, it can be aluminum, doesn't matter. So for the 500 turns you do a 3 to 4 turns of a primary. What I've done is just wound it here. You can see this black duct tape which is sealing the wire. Here is the output of the wire, and this is the second terminal of the wire. It doesn't matter where you wind it over the length, across the length, as long as it is wound. It doesn't have to be tight or doesn't have to be anything. You can just wind it easily. Now, an important aspect of the primary and the secondary is that the direction of wind has to be opposite to each other. If, for example, if looking down from top, if your secondary is turning around in clockwise direction, then your primary should turn in anti-clockwise direction. This is just because you want to have additive polarities. This is an electrical engineering concept for transformers where you have additive polarities which will help in getting the voltage stepped up. If you do not wind it in the opposite direction, it will be subtractive polarities and you will not get the light to lamp up. The lamp would not light. Okay, so this is an important aspect. Okay, got it. Now, since we built a transformer, as we all know, transformers don't operate on DC supply. They need an alternating current supply. Now, an option to do is across these two terminals you could directly connect the AC mains of our household supply. But whoa, that will be very risky. You know why? Because it's 240 volts, and if you, at 50 hertz, if you step it up, the step up ratio is 500 divided by 3 to 4, so it's kind of more than 100 times. So you're going to get 2400 volts of air alternating current here, which is going to be lethal. It will kill you, you know. So that is absolutely not advisable. So for hobbying, as a hobbyist we are, what's the safe thing to do? The safe thing to do is use 12 volt direct current supply. But then we just said that a transformer does not work on direct current. And again we said that for safety reasons we have to use direct current supply. So how do you, these are kind of contradictory requirements. How do we overcome these? Well, for example, if I put a direct current supply across these two terminals, and by some mechanism I am able to switch it on and off many times, it is essentially creating an alternating current, because the polarities go up and then drop down to zero and go up and drop. So it's kind of a wave, okay, something like this. So if we can get that mechanism put in place, then we can have a safe alternating current supply through our safe 12 volt DC supply. Now, so to achieve that, what we need is something that will switch on and off that DC supply with a high enough frequency to be able to register alternating current here. So the easiest way to do this is use a transistor. Now, for those who are not initiated with the working of transistors, like I was not, I'm a mechanical engineer, so I am not very strong in electronics, so I learned it, is that transistor has three terminals. One is a base, one is a collector, and one is an emitter. Now this is an NPN transistor. You could use a PNP transistor with a different configuration, and we won't get into that, but just suffice to know that I've used a MJE3055T, which is an NPN transistor. Now the way a transistor works is it works like a mechanical valve with a trigger. When I supply, the trigger is a supply voltage on this base terminal. When I supply a base voltage, what it does is it opens up the wall between the collector and the emitter, and it lets the current flow through the collector to the emitter. And when the voltage across the base is switched off, then the current across the voltage across the C and E stops flowing. So a base voltage is like a tap wall. When I open the tap wall, the water starts flowing from collector to emitter. When I close the base wall, the water does not flow from collector to emitter. That means if I am able to somehow switch on and off the supply to base, it will switch on and off the supply across the primary and the secondary. Cool, that is nice. So how do I do this? It's very simple. So if I look at the schematics from a little far away, what I've done is, this is your 12 volt DC supply, from which the positive end is connected to a base via a 30 kilo ohm resistor. Now why did I use 30 kilo ohm, and why did I use a resistor in the first place? There are two reasons for this. Number one, the resistor serves as limiting the current that flows to base. In case you are using a lower threshold transistor, you don't want to burn the transistor by sending in a lot of high current. Our usual charger current is 2 amperes. So what you do is V upon I, voltage upon resistor, Ohm's law. So if our voltage is 12 volt, you divide by 30,000 ohms, you're getting sufficiently low current to protect your transistor. So that's number one reason. And number two reasons you will come to know in a while. Okay, so let's see, if we connect the positive end of the battery or the charger via a 30 kilo ohm resistor. I'll show you how I did it here. You can see this. This is the positive end of the battery, and this is your 30 kilo ohm resistor here. Okay, and then it goes into the base. Okay, now when the base has a voltage applied, it will open up the collector and emitter. So from this, the voltage now flows through the primary and comes to the collector and now since the base has already current applied, so the collector current can now flow to emitter, and from the emitter the circuit is completed. But here is the fun part. The fun part is that because now it has taken a path of least resistance through the primary. Remember, we have added a 30 kilo ohm resistor, which is now creating a path of higher resistance for the base, and the primary path is now a path of lower resistance. So the current or the voltage prefers to flow from the primary winding through the collector and emitter rather than flowing from the 30 kilo ohm resistor into the base, and thereby as we always know, electricity flows to the path of least resistance. So it ignores this path, and now suddenly the base terminal of transistor has no voltage applied to it. So remember what happens when the no voltage is applied to the base. The collector and emitter gate opens up, and now the current stops flowing from here, and suddenly now this path becomes a path of low resistance, and the voltage starts flowing back again in base, and again the same rigmarole happens, and the collector emitter goes becoming a path of least resistance. This path stops and the base voltage stops and opens, and you will see now this happens at a very high frequency, and thereby successfully converting our DC supply into on and off alternating current supply through this mechanism. Okay, and as we all know, because there is a alternating current supply in here, this will induce a secondary voltage equal to the ratio of the number of secondary turns to the primary turns, which is more than 100 times. But then you might see there is a wire from secondary that goes down and connects to a diode, and the diode seems like it has been connected in the opposite manner. So the positive end of the diode, the longer leg, is connected to the negative of the battery, which typically doesn't happen, but there is a reason why. Now there is a technical reason. The Slayer exciter circuit or Tesla coil is a resonating circuit, and for resonance and resonating, you'll have to figure out what is the natural frequency. So if the natural frequency of these two windings is somehow made to match, or the flow of electricity in these two windings is somehow made to match with the natural frequency of these two windings, then you will get a double amplitude or maximum output. Okay, and so what we do is we connect this secondary wire through the diode to the base. What it does is it gives a feedback loop to the transistor. So it also tells that when the base current is switched off from the earlier explanation, and if there is a voltage in secondary, it will still keep the base voltage on and let the flow of electricity from collector to emitter. And this is how it tunes itself to match the frequency of the voltage passed here to the frequency of the secondary, and this is how the resonance is achieved. Now if you find this explanation complicated, doesn't matter, it does not matter, just suffice to know that we have to somehow get the feedback from the secondary to the base via a diode. Then why did I use a diode? Why did I not connect it directly to the base? Is because the diode, as we all know, is a unidirectional wall. So we do not want, if I directly connected this wire to the base, what would happen is then the DC supply would go into secondary instead, because it will have the path of least resistance. Okay, so we don't want that to happen, which is why we only want it to go one direction and not the opposite direction. And so this is basically the schematics of it. When we turn this on, you get induced voltage in this to a tune of around 1200 volts. But then you might argue that why is it not dangerous now to touch, because it's 1200 volt. But remember the old maxim, volt jolts and current kills. So even though the volt is high, it will just give you a jolt. If you touch the wire, you can safely touch the wire, but since the currents are in milliamperes, it's not high enough to be lethal or cause a long lasting damage. You can use a neon light, you can use a CFL. My CFL lights from around 3 to 4 inches. An important point I forgot to mention is that in doing all this tuning and switching on and off, this transistor, as you can imagine, is doing a lot of work, switching on and off many times in 1000 hertz, 1000 times a second or whatever. This thing gets very hot, so you're gonna have to have a heat sink applied to this transistor to make sure that the heat is taken away, is dissipated. Okay, that's about it. Nothing complicated. You can use this layer exciter circuit as a first step to start your hobbying of Tesla coils. I know this is not a real Tesla coil, but this is a good starter for whoever is interested in building the Tesla coils. After this you have built, you can then jump on to the solid state Tesla coil, which is spark gap controlled, and then plasma bulb and all that stuff. But this is a good starting project for all you hobbyists out there wanting to make their own Tesla coils. I hope you enjoyed this. Do subscribe to my channel for more videos on physics, and do not forget to hit like if you like it. And of course, as always, ask your questions in the comments below. If I know the answer to them, I'll answer them. If I don't know, I'll try to find out, or if I still can't find out, I'll let you know that I can't find out the answer. We all can collectively find the answer otherwise. All right, happy physics projects and have a good day. Bye bye.